Swayam Prabha. Digital India. Educated India.
In the last class we were discussing about hybrid rockets. In this class let's look at how the burn rate relationship A GOX to the power of n is obtained. Okay. So firstly, to do that we need to understand how the burning takes place inside a hybrid rocket motor. Now if this is the hybrid rocket motor, then oxidizer is injected here, right. So a boundary layer develops and the combustion takes place inside the boundary layer. Okay. So this is how the combustion takes place inside a hybrid rocket motor. Now if we look closely into this combustion zone, then we will be able to look at what are all the processes that are taking place in that zone. So let's say this is the solid fuel that we have. Okay. Then let's say we have taken somewhere in this region, right, where the boundary layer is already established. So this is the boundary layer, and let's say this is the flame zone, right. Now what is happening, because of this boundary layer there is a heat transfer to the propellant which is convective in nature, right, and that heat transfer is being taken up partly for maintaining the temperature profile in the condensed phase, and then partly to evaporate the fuel. So if we were to draw the temperature profile inside the boundary layer, it would go something like this. This is Ts, this is Tc, and this is Te. The combustion that is achieved here, the temperature that is achieved here is the highest, simply because there is combustion, and after which it is diluted by oxidizer, right. Now the propellant burns in this direction, and there is, because of that, there is a mass addition that is given by rho p r dot. Okay, mass is getting in, and there is something known as blowing effect that we had discussed when we were discussing about erosive burning in solid rockets. Now, so there is heat that is being transferred, let me call it as QC, okay, that is heat that is being convected into the propellant surface. Now this QC, I can write it as H into Tc minus Ts, okay. This is the convective heat transfer coefficient, and this is the adiabatic flame temperature or the combustion temperature, and this is the surface temperature. Now this heat, as I said, is part of it goes to maintaining a temperature profile and part of it is used for evaporation. So QC must be equal to let me call this direction as X and this direction as Y. So okay, this is the temperature, this is the part of the heat that is taken up to maintain the temperature profile, and this is the QS we had seen earlier is the heat of evaporation at the surface. So this we had seen with regards to solid propellant that we can rewrite this part as rho p r dot Cp Ts minus T infinity. Let me call the temperature here as T infinity. So I can rewrite this as QC must be equal to rho p r dot okay. Now for ease of our terminology and other things to follow, let me call this part as HV. Okay, HV is nothing but Cp Ts minus T infinity plus Qs. Now we know that this problem is a boundary layer driven problem. Okay, so what we are going to use is something known as Reynolds analogy. What it says is there is a similarity between the momentum boundary layer and the thermal boundary layer, right? And we use that, it is easier to calculate the momentum boundary layer, there are correlations for it, and we use that to calculate the thermal boundary layer. This can happen when only what? Prandtl number is close to 1, which in gases it is always close to 1. So we can make this assumption. So using approximate Reynolds analogy, that is, there is similarity between momentum and heat, or momentum and energy, so we can define something known as a Stanton number, UE is nothing but the velocity here. Okay. So H is the heat transfer coefficient, rho E is the density at the beyond the boundary layer, and UE is the velocity beyond the boundary layer, Cp is the specific heat. This is a non-dimensional number. It is also known as dimensionless heat transfer coefficient. Okay. Now if we use the Reynolds analogy, what it says is that this Stanton number indicated by Ch is equal to Cf by 2 where Cf is nothing but skin friction coefficient. Okay. And we know that Prandtl number is close to 1 for gases. So this term becomes merely Ch is equal to Cf by 2. Now we have defined what a Stanton number is, and we have found out that by Reynolds analogy we can equate it to this skin friction coefficient. Now if we multiply the numerator and denominator of the Stanton number by a delta T, that is given by Ts minus Tc minus Ts, okay, we will do that and see what we will get. So we had Stanton number Cf is equal to H by rho E UE Cp. So we will multiply both numerator and denominator by Tc minus Ts so it doesn't change anything to the left hand side. But what is H into Tc minus Ts? Huh? That is the convective heat transfer, right? So Qs is equal to H into Tc minus Ts. So what we will end up getting is, sorry, this is not Cf, Ch. Huh? Ch is equal to this. Huh? Which one? Oh, okay. Okay, sorry. QC. Fine. Now, what we need to, this part is QC. So, what is this part? We can define it as some change in enthalpy. So, we will call the delta H is equal to Cp Tc minus Ts. So, what we will get is we also had the other term, that is the heat that was taken up by the solid. Let me call that as Qs, that was equal to rho p r dot hv, right. But we know that these two must be equal, right. That was the heat balance at the surface. For the heat balance at the surface, these two must be equal. So, I can now replace in my Stanton number definition this here, right. So, and Stanton number, this also I know is nothing but Cf by 2, right. So, I will use that. So, I will get rho p or Cf by 2 is equal to rho p r dot hv fine. Or in other words, I can rewrite expression for r dot as r dot is equal to Cf by 2 into rho e ue delta h by hv, okay. Sorry, divided by rho p. Now, we have been able to get this expression for r dot in terms of rho e into ue is nothing but in some sense mass flux, okay, and Cf by 2. What we need to further determine is what is this Cf for the particular geometry that we have considered. So, skin friction coefficient without blowing we can write it as Cf naught by 2 is equal to in terms of Reynolds number. This x indicates the location along the axis. Okay. This is for a turbulent flow. Now what happens because of blowing is the boundary layer in a sense tends to get thickened. Okay. So the skin friction with blowing will be different. And it can be given as Cf by Cf naught where beta varies from 5 less than half. Okay, beta is nothing but the blowing coefficient. And we can define beta as follows. Beta is defined as rho p r dot, that is the mass flux that is coming in from the surface to the mass that is going through the port. Okay. It is also known as non-dimensional So we have defined Cf in terms of Cf naught into beta, and we have beta. So we can now get the expression that we were looking for, that is we had said that Ch is equal to this is nothing but rho p r dot hv by ue, that is this expression, right. So we can use this expression. If you look at this expression and the expression for beta, right, there is some similarity between the two, and we can write delta H by HV, it is nothing but rho p r dot that is equal to beta, right. So now I have this expression for r dot here, wherein I have defined Cf, I have defined all other terms, so I can get plug them in and get my expression for r dot, which we will do. R dot is equal to Cf by 2 rho e ue by rho p right. Now we know that Cf is nothing but Cf naught into beta. So we will use that here and get our expression for R dot. So R dot is equal to 1.27 by 2 into Cf naught into beta to the power of 0.77 into rho e ue by rho p into beta. Fine, because we know that delta H by HV is nothing but beta. So Cf naught also we know in terms of Reynolds number as this expression here. So if we substitute that, we will get R dot is equal to so beta is minus 0.77 and 1, so I can write it as beta to the power of 0.23. Reynolds number is nothing but rho e ue into x divided by mu. So I get R dot is equal to so we have rho e ue here and here, so we can club those two and rewrite our expression as R dot is equal to, and I can take the rho p that is here, this rho p I can multiply it back with the R dot, so I will get rho p R dot is equal to what is rho e ue? Rho e ue is nothing but the mass flux in the port, right? So mass flux let us define G as m dot by AP, so that will be nothing but rho e ue so you have, we can replace this with G, right, and we will get minus, yes, thank you. So we come to this expression, there is a 0 here. So we get this expression wherein the burn rate is related to the mass flux through the port, right? And if you look at when we do experiments, it is easier to characterize this in terms of the oxidizer mass flux itself, because that is something that we have control of and we know what it is. So which is why you will find that if you take a look at any hybrid literature, you will find that the burn rate is expressed as a function of GOX. Okay. So we can recast this in terms of GOX, and that is what you will find in most literature as R dot is a function of GOX to the power of n. And if you look at this expression, you will find that it depends very weakly on x, the axial location, and beta, but it is a very strong function of the mass flux. Right. Now let us look at the problem that we had said yesterday with regards to what happens to burn rate as we proceed in from the head end to the nozzle end. If you look at this expression here, it looks like what should happen to the burn rate as you increase x. It should decrease, but I had said the opposite yesterday, right? Is that correct or is that wrong? Huh? If you look at this, yes, you are saying, but you are forgetting that there is a greater dependence on G. If you look at what is happening as you move from the head end of the port to the nozzle end, there is continuous mass addition, and this is increasing as you go from head end to the nozzle end, and this is raised to a power of 0.8. So therefore you will find that the burn rate as you go from head end to the nozzle end will always increase. Okay. Now people have done people have conducted experiments and found out that if you take the oxidizer mass flux, the dependence of burn rate varies, this n varies from 0.4 to 0.7. One of the things that we have kind of made an assumption right at the beginning was we had assumed something like a flat plate, if we assume a pipe flow kind of a situation and redo the calculations, we will probably get closer to what is observed experimentally. Experimentally, what we can get is in terms of the oxidizer mass flux and not the overall flux. Okay, overall flux involves that you take a cross section and find out what is the fuel plus oxidizer that is coming in, which is a lot more difficult to do if you are doing an experiment. You are better off knowing what is your mass flow rate of oxidizer and then calculating the oxidizer mass flux. There was another problem that I said hybrid rockets suffer from because of this N, that is, if you look at holding even when you hold the oxidizer mass flux constant, we find that the fuel mass flow rate was changing. Now let us look at, is there any condition at which the oxidizer mass flux, if you hold constant or if you hold the oxidizer mass flow rate constant, will the fuel flow rate also become constant? We know that the mass flow rate of fuel is given by rho p AB into R dot. So if you are taking a port configuration, rho p into, this is the diameter of the port, and this is the length of the port. This is the burning surface area, into R dot is nothing but A into, okay. Now let us determine what value of N will give us something that when you hold the oxidizer mass flow rate constant, you can also get a fuel mass flow rate constant. If we have to engineer such a hybrid, then that is a very good situation, because you can operate it at a set specific impulse even though the diameters are changing. So GOX we know is nothing but fine, this is GOX. So if we plug it into this equation, we will get m dot f okay. Now this is you have 2 into n, right, in the denominator, and if you look at this equation, you have d to the power of 1 and d to the power of 2n. And it is very obvious that if you have a value of n that is equal to 0.5, for n equal to 0.5, m dot f becomes independent of the port diameter. So, therefore, you can operate it at a set O by F ratio, so that you can choose that O by F ratio such that it gives the maximum ISP. Now, what happens if n is greater than 0.5? So, it is desirable to have n equal to 0.5. Now, for n greater than 0.5, what will happen to the mass of fuel? As diameter increases, it will reduce, because you will have 2n and you will have dP here. So, the denominator will be greater than the numerator. So, therefore, as diameters increase, mass flow rate of fuel will decrease. And similarly, or for the other case, that is for n less than 0.5, m dot f this finishes our discussions on hybrid rockets. So, in a sense, we have learnt three kinds of rocket engines in this course. That is, one is solid propellant, the other one is liquid propellant, and then lastly the hybrid propellant. Okay. Thank you.